www.nanohub.org. You can follow along with this presentation using printed slides from the NanoHub. Visit www.nanohub.org and download the PDF file containing the slides for this presentation. Print them out and turn each page when you hear the following sound. Enjoy the show.
I'll just begin talking about the interface charges and then pick up the real meat of the discussion in the next class. Now, one thing you realize that this interface between silicon and silicon dioxide, that region is a very complicated region. You know, silicon part you understand. Diamond lattice, do you remember from long back, diamond lattice, 1/4 the body along the body diagonal and everything. Silicon is beautiful. Every electron where they're supposed, or every atom where they're supposed to be, very nice. But as soon as you go to the oxide, first of all, oxide is amorphous, meaning they are in random places. So that's what I have shown here, that the silicon and oxygen, they are sort of randomly configured. And then there are also dangling bonds like silicon hydrogen, and I'll explain in a second why they come. I've shown on the top how a silicon oxygen bond, silicon dioxide, actually looks like. So the little tetrahedra with 4 red circles, just focus on one element. With 4 circles around, this reds are oxygen. And little balls inside which is a, let's say, a whitish color, that one is silicon. Silicon binds with 4 oxygen, right? So it binds with 4 red atoms, do you see? And every red atom, every oxygen is sort of bound by between 2 silicons. Every red, look at every red. Every red has 2 silicon atoms, the white atoms, sort of connecting it up. Therefore, you have silicon dioxide because every silicon connects to 4, but every oxygen is shared between 2. So as a result, effectively, every silicon has 4 halves, right? 4 halves, and that gives you silicon dioxide. So this is the amorphous structure of silicon dioxide, this random networks of tetrahedra. This is not diamond lattice. Diamond lattice doesn't look like this. This is a tetrahedra, but it looks like very different from diamond lattice, right? So that's silicon dioxide. So anytime a oxygen is missing, that's a trap. That's where all those charges were being trapped before, in what I was showing you before. And each were the tetrahedra, that's what I wanted to make. The oxygen is a red, and that's being shared between 2 silicon, that's the ash-colored atoms. So you can see why this is called a silicon dioxide. Many times again, you will put it on a flat surface because it's difficult to draw in 2 dimension and draw correspondingly. And I have shown you before, right, how the tetrahedra, you pull out one tetrahedra out and lay it flat, and this has the 4 covalent bonds. I have shown you before, but you realize that the atoms on the surface are unsatisfied because everybody has sort of 4 nearest neighbors. Atoms on the surface, how many did they have? They have sort of 3, and one of them is sort of dangling. And that's not a good thing. Anytime say, a bond is unattended, that can cause trouble. And what happens, do you remember that we calculated how many atoms do I have on a surface, 1, 0, 0 surface, 1, 1, 1 surface, do you remember? And because those bonds are dangling, those bonds can capture electrons. So those will all come as surface states. Do you remember the surface state, surface recombination velocity and all? So this is those from exactly from that diagram. So you will have a series of surface states because the crystal is no longer periodic. You're stopping it. As a result, you will have a series of dangling bonds which are not the solution of the periodic Schrodinger equation. How many do I have such dangling bonds? Okay, you have done this in a homework. How many? How many could it be? Number of atoms, silicon atoms, is on the order of 10 to the power 22, 23, right, per centimeter cube. So if you just make an estimate, number per centimeter squared on 100 surface would be on the order of 10 to the power 14 per centimeter squared, and if you didn't do anything, that is the number of defects you would have had. That's the blue line. That's the blue line. Number of defects you would have had 10 to the power 14 per centimeter squared. That's huge number of defects. No hope that a freely exposed silicon will carry any current through its surface. No hope. Every one of them will be caught by those dangling bonds, because it wants another electron. Wherever it gets it, if it's going from source to drain, it will catch it and keep it for itself. So this is going to be a horrible situation. So when you put the silicon dioxide, remember that silicon, the tetrahedra I just showed you, silicon shared between 4 oxygen and the oxygen being shared between 2 silicon. Remember the previous picture? So that has been laid flat on the page, and that's how it looks. So as soon as you bring oxygen, a bunch of those dangling bonds are satisfied because they take care of it. But the silicon dioxide has a different lattice constant than silicon. Therefore, not all of them are satisfied. You can see that the oxygen has taken care of some silicon, but a fraction of them are still dangling. And therefore, when you oxidize, it reduces the density to 10 to the power 12, right? Because many of them have been taken care of the oxygen, but still 10 to the power 12, one would be dead with 10 to the power 12 number of centimeters squared of interface traps. So then that is the story of 1960s, that they then spend a huge amount of time to push this interface defect density down to 10 to the power 10 nowadays. Now, what is generally done in this case, that if you have a lot of dangling bonds on the surface, silicon surface, then of course the first thing one would do is to bring down the silicon dioxide. And this is the flattened version of the silicon dioxide, where you see the silicon being sort of nestled between four atoms, oxygen atoms, and every oxygen being shared by 2 silicon. And that gives you the formula silicon dioxide, because silicon, half of the 4 each one gets, and that's why it's silicon dioxide. Now, of course, what it does is that what you can do then is do this anneal. It's called a forming gas anneal. Forming gas anneal means that once you have grown the silicon dioxide, after that you put it in a chamber where you bring in some form of hydrogen atoms, some form. So there are various ways. You can bring in silane, on various compounds you can bring in. But the bottom line is you bring in that hydrogen molecule, or hydrogen molecule which reacts on the surface, and then every hydrogen sort of ties up the dangling bonds. And you realize it had one dangling bond. Hydrogen has 1 electron, 1 proton, and it's a small atom, so it can get through anything, and therefore they will come down and essentially passivate all those bonds. And now all the silicons are satisfied. Electrons can go unimpeded from source to drain without being sort of trapped by the dangling bond of silicon. Now this process is very important, but even before that, so first of all, this will reduce it to a tremendous amount. But even before you bring in silane, what is done at many times is that this processing of silicon dioxide, the growth of silicon dioxide, generally has to be done at a very high temperature. The temperature you see here in degrees centigrade is 1100 or 1200 degrees C. And that will give you, look at the plot, it gives you about 2 times 10 to the 11. Here you have not yet done this hydrogen or forming gas anneal or the passivation, not yet, but you still have 10 to the power about 2 times 10 to the power 11 even when you anneal it at 1200 degrees C. And it's very important that you keep the anneal temperature very high, because if your anneal temperature is low, then the number of defects that you have or dangling bonds that you have in the surface can be a very large number. One thing I want to point out, that this is 111 surface. That's where the experimental data is reported from. But if it is on 100 surface, it will be 1/3 less. And this is something you should understand, because this is something people often ask you in various interviews and other things, that why is silicon is on 100 surface, although in many cases 111 surface might have better mobility, right? It could have better mobility. The reason is that when you cut in terms of 100 surface, the number of bonds you have per centimeter squared is actually less, and that therefore the number of dangling bonds are less, and as a result you have less trap on 100 surface, and therefore people prefer to do it in 100 surface. But here it's a 111 surface and you have that certain number. The interesting thing is that if you anneal it at a particular temperature, and then anneal simply means heating it up, just putting it in a chamber, a piece of silicon, and raise the temperature of the furnace. Like in a microwave, you put something in, raise the temperature. So raise the temperature, and if you do that, then essentially the number of defects will go down. Now these are essentially broken silicon bonds which are about to react with oxygen that was coming down but didn't have a chance to. So high temperature helps in the reaction process. Now the best one is, of course, if you always anneal it in the ambient nitrogen or hydrogen environment rather than pure dry O2. So in that case, you can see you can have a flat region even at lower temperature, let's say 800 or 900 degrees C, because it ties up all the bonds on the surface. Now once you have done it, then you can see the defect density might go from 10 to the power 12. You can see the blue curve, which is add oxidized, and do you see between these two? So this is saying that in the mid-gap region, remember the mid-gap regions are the ones that are most interesting. We're talking about traps, right? Do you remember Shockley-Reed-Hall that if you have a lot of traps close to the conduction and valence band, doesn't matter. The ones that are most effective for Shockley-Reed-Hall recombination or surface recombination are the ones that are in the mid-gap region. And you can see here that number is on the order of 10 to the power 12 if you do not do any forming gas anneal or do not tie it up with hydrogen. But as soon as you do so, you can see that the number reduces to 10 to the power 10. And this today is what you need in order for an operating good MOSFET that you can buy for your Pentium and other processors. Numbers on the order of 10 to the power 10 number of states per centimeter square. Now, when this defects goes from 10 to the power 12 to 10 to the power 10 after this hydrogen passivation, now these defects correspondingly, the signature of it, that you have been able to reduce the number of defects, is also reflected in the CV characteristics. You can see here on the bottom right hand side that I have plotted the capacitance as a function of gate voltage. Now, do you see that this capacitance is flipped? Because all the capacitances that we had been looking into, accumulation was on the negative gate voltage because the substrate was p-type. Now, this particular experiment, I have taken it from the book, or particular diagram, I have taken it from the book. In that case, the substrate is n-type. If it is n-type, then you realize that all the voltage polarity required to see accumulation, depletion and inversion, those will all get the other way around. And you can see that before you have a strange CV curve that goes from, it has the accumulation on the right hand side to a particular value. Do you notice that C divided by C naught is equal to 1, because in accumulation the charge is just sitting next to the oxide, so that's why you have it 1. And then as you go through this threshold flat band region and gradually go to the accumulation region, the inversion region, then you can see that on the other side, starting from minus 10 volt, this is essentially flat and at a lower value of capacitance. What frequency is this? This is at relatively high frequency, right? Because this is not a high, otherwise it would have gone back. And this is a capacitor structure. How do you know? Because in transistor, you would have never seen that the flat region which is at high frequency, because in transistor high frequency, even at high frequency, it goes back to 1, right? Threshold voltage minus 10 volts here. Do you see that? That's where it becomes flat. All right. Now, this blue curve corresponds to that very high defect density, 10 to the power 12, let's say. what happens that after you anneal, the effectiveness is reflected by the sharpened, by much sharpened the rate CV characteristics. And you can see it remains flat for more regions. The flat band is close to 1 and the threshold voltage has gone down significantly. Do you see that? It's about -2, -3 volt. And this has happened because all the interface traps that were trapping charges before, you know, this QF and QIT, that was the interface charge, those have been taken out. Therefore, your threshold voltage has gone back. Now, this is very important that you understand the physics of this stretch out. This is called, this blue curve is sort of looks like you have stretched the red curve out. So that's why it's called a stretched out CV. It gives you a lot of information about the status of the surface. Remember, surface is everything. In MOSFET, surface is everything. And so that gives you a status. So we want to understand why this blue curve looks like this. Why is it stretched out like this? So that is what I want to explain to you. Now, this is very important to understand that just like donors is an atom, let's say, which gives away electron, right? Close to the conduction band gives away electron. Every trap have very similar characteristics. But in this particular case, these donor levels, the surface levels, of course, they are spread throughout. Look at the left-hand side plot. I have plotted the conduction and valence band, and I have plotted the just close to the interface between silicon dioxide and silicon. Now, the blue and the red, these are actually the same surface states. Now, the dotted line is the Fermi level. Now, this is, let's assume that these levels are donor-like. These are not donors. These are donor-like. What it means is that, you know, when your donor level is below the Fermi level, then the donor is full, right? Because it hasn't given away its electron. When a donor doesn't give away its electron, then it has as many protons as the number of electrons. Therefore, because it hasn't given away anything, therefore, anything below that dotted line, Fermi level, is charge 0. It has not given away its electrons full, donor levels, therefore, is charge 0. What about the ones above, which are the red dumbbell shaped thing? What about them? Those are above Fermi level. In above Fermi level, typically these are Fermi function is 0. Therefore, they are empty. And if the donors are empty, then these are positively charged. Okay. Look at the, so if that happens if it is donor-like. If, on the other hand, look at the middle panel. Let's assume now that these are not donor-like. These are acceptor-like. Now, in this case, what does an acceptor do? Again, you see in the middle panel, the dotted line being the Fermi level. Below, sorry, the levels above, the blue lines, small blue lines, in those cases, those are empty, right? Above Fermi level, they are empty. If they are empty, that means they have not caught any more electrons. So in that case, what will happen? Those will be 0 charge, because an acceptor, until it catches an electron, right, it's charge neutral. Okay. Now, on the other hand, if it is below, then it's full. It full means, remember, it has one extra place for one extra electron in the outer shell, right? That's what the acceptor is. Like boron is an acceptor. So it catches one electron. It's full. As a result, everything that is below for acceptors is negative, right? It takes a minute to think through this, but you get the idea. Now, what happens that many times these levels, depending on how the hydrogen bonds are oriented in different direction, may either behave like a donor level or an acceptor level. So in general, what I have seen on the right hand side, that generally you will have a combination. Now, do you realize the dumbbell shaped blue ones, these will be positively charged, right? I'm sorry, those would be neutral. Neutral because below Fermi level donor like, and the dumbbell shaped red ones, those will be positive. And similarly, what will happen to the short red segments on the right? these would be below the Fermi level. That means those will be negatively charged, because these are acceptors. When they have an electron, extra electron, then they are negatively charged. And so from here, depending on the Fermi level, you can see I can tune how many positive and negative charges I have on the surface, right? And that will give me different amount of threshold voltage shift. So that's what I'm after. So let's see what happens. Now follow with me carefully, because this is something the professors like very much, and let's see whether I can explain to you. What type of substrate I have? This is a N-type substrate. So therefore you can see my CV characteristics is facing to the other side than what I typically draw. Now let me assume that these are donor-like, all donor-like traps. Now I have bent the band, I have applied a positive bias. So now the N substrate is in accumulation, because it has brought closer to it all the electrons, majority carrier. Now the level, all the defect levels are below the Fermi level. They are all full. If they are all full, what is the total amount of charge? 0. Donor levels all full, below the Fermi level, 0 charge. If it is 0 charge, then of course I have whatever my classical standard CV characteristics is, no problem. If it stayed 0 throughout the voltage swings, then I would have this ideal red CV characteristics. However, what happens that as you go up, by the way, on the top side I have written alpha Vg multiplied by Qox, because this amount of charge depending on the bias will be changing. And so alpha, the fraction of the total number of defects that contributes to the charge, that will be changing depending on the bias there. Now let's say I'm beginning to go the other way, beginning to deplete, right? So I have to apply a negative bias because it's an N substrate. Now as I am beginning to deplete, a fraction of the charges, fraction of the defects have moved up the Fermi level. Do you see that? Therefore, now I have some charge contribution which will change my threshold voltage. As a result, if this fraction, for example, if it remained the same throughout for all voltages, then I would have a fixed shift in the threshold voltage associated with this amount of charge. So I would have this blue curve. If this was constant, I'm not saying it's constant everywhere, but if had it been constant, this amount of charge, then I would have a fixed shift in the threshold voltage, and you can see the blue curve has shifted. A little bit more, if I now try to invert it, invert the substrate, all the defects are up above the Fermi level, everybody is positive, huge change in the threshold voltage. So I will have the final curve over there. Now it's supposed to be, the first curve was supposed to be magenta and the last one is red. Hopefully you can see that. Now, of course, this is going through this phase is as a function of voltage. So as if the threshold voltage keeps changing as you keep pulling the bias, as if the threshold voltage keeps changing. So the real curve you will be seeing is not these separate three curves. Of course, what you will be seeing is that there will be a transition of this curve among these curves from one to another. Now do you see? You have stretched things out. Now I have just shown you three discrete points. Of course, it will be a continuum of points, and you can see therefore the green will become a continuously stretched out CV characteristics. You see that, right? Okay. So that is for the donor states on this side, on the the depletion and the inversion side. But if you have acceptor states, that will give you stretch out on the accumulation side. This is how. Now, if it is acceptor-like, then what happens? Then, if you are on the starting from now for this CV characteristics, I am starting from the very right, because look at the band diagram. I have applied a large negative bias close to inversion, right? It's close to inversion. Now, this is acceptor-like. All the states are above Fermi level. As a result, they are all empty. And if they are all empty, empty means, acceptor means it has not accepted any more electrons. It needs electrons. Therefore, the charge is 0. So the CV characteristics is ideal CV characteristics, no problem. Now, as you are going the other way, because now you are sort of going from the accumulation, trying to come the other, starting from inversion, going to the other way of accumulation. Then as you move down, then of course you have a bunch of acceptor states below the Fermi level. Now these are negatively charged because they just accepted an additional electron. Remember, when boron catches an additional electron, that is when it becomes Na-. So therefore I will have some negative charge, and when I have negative charge, correspondingly the threshold voltage, if you put the values in, it will move to the positive side. So now this will be your threshold voltage. Do you see that? And then if you really try to accumulate it, go to the other way, everything is below Fermi level. All acceptor states, full negative, impact of full negative. The curve has completely shifted to the right. Again, because of these charges, you will have this transition going, because this is continuous process, right? So due to acceptor states, therefore, you have a corresponding stretch out here. And so when you pull them together, then you see that you have a continuous, if you have a combination of both present, donors and acceptor present, then you will have this stretch out that will go continuously. Now there is I show a discontinuity over there, that there will not be any discontinuity because you will sum them. You will sum them, so therefore the effect will sum up. I have shown them individually, therefore there is a discontinuity over there. And that's what your before annealing CV characteristics is. Now I'll tell you all about hydrogen passivation and other things 2 lectures down, but for the time being, this is very important to understand that anytime if you see a stretch out, you have to improve your surface, and then you go and try out various strategies to improve your surface. This has got nothing to do with silicon per se. It could be gallium arsenide. If you have donor and acceptor like surface states, you will have the same problem. It could be graphene, or it could be anything. And this stretch out simply reflects the fact that there is a voltage dependent charging of the surface states, and somehow you have to fix it, because otherwise your transistor isn't working. And so the strategy will be different. Here hydrogen passivation works, other places there are other things that people have done. So to conclude this lecture, so we are talking about non-ideal threshold characteristics, and obviously it's a very important thing for MOSFET design. And this non-ideality arises from wide variety of sources. Your choice of substrate and the gate metal, aluminum, germanium, copper, silicon. This combination dictates what your work function is going to be, and in many cases this is a good thing. I'll show you later. And trap charges, what are these trap charges? These are essentially charges that could be sodium, moves back and forth. These days it doesn't happen, because of course you are not allowed to get into that room anyway. These are robots, will essentially say thank you, you can stay outside. They will do all the handling, and they don't have sodium chloride in their hands. So therefore you don't have that problem, but there are other problems. But the interface states is a very fundamental problem. Then these almost there is not too many good ways to handle it. Hydrogen passivation is one very effective. And these are all discovered in 1960s, by the way. And that made the first Intel transistor processor possible in early 1970s. All in Fairchild, as I said before. And now there are other non-ideal effects due to transistor degradation, and I will show you in that 2 class down how this works.